Let's use the simplex method to solve this linear programming problem. Notice this one has 3 decision variables, which means it would be impossible for us to do it using the graphical method. In the graphical method, when we are drawing our lines, we are limited to 2 variables so that we can use the x-axis and the y-axis. What the simplex does in this case is sort of a 3-dimensional analogy to the 2-dimensional graphical method. In other words, we can still think of corner points even in 3 dimensions. We just have a 3-dimensional spatial object. When we get to 4 dimensions, we can't even visualize it at all, but the simplex can still use the same process to do it. So this is a good problem to use simplex. Here again, we will do the row operations individually because you should know how to do them, but I would strongly encourage you to learn how to use one of the many technological tools available to you to speed up your calculations on the simplex method so that you don't have to do the row operations by hand every time. Let's start by writing our initial system. Each of our inequalities we will want to rewrite as an equation by adding a slack variable. So this first one we will have 2x1 plus x2 plus 2x3, and now we're going to add our slack, so I'll call that slack variable number 1, s1. That's equal to 14. Next inequality, 2x1 plus 4x2 plus x3. This time I'll add s2, and it'll add up to 26. Third inequality, x1 plus 2x2 plus 3x3 plus s3 is equal to 28. Let's go to our objective function. I'll write it up here, but remember you'll put it on the bottom row of your simplex tableau. So we're going to subtract 2x1, 2x2, and x3 from both sides. That will give me negative 2x1, negative 2x2, negative x3 plus p is equal to 0. And of course, our x1, x2, x3, and all of our slack variables, s1, s2, and s3, all of these are bigger than or equal to 0. We call this the initial system. From it, we're going to write our initial tableau for the simplex method. First, I'm going to label my columns with the variables. And the last column will be for the right-hand side. I put in my coefficients, 2, 2, 1. I'm going to put my objective function on the bottom row. That's rather an arbitrary choice. There are some people who like to put it on the top row. The process works the same no matter where you put it. These are my constraints. So for x2 I have 1, 4, 2, x3, 2, 1, 3, s1, and in my constraints I don't have any p's. I have 14, 26, 28, and I'm going to go ahead and put that objective function in. So negative 2, negative 2, negative 1. No slack variables in there, so those are all zeros, plus 1p is equal to 0. Okay, this is our initial simplex tableau. Sorry, just move that out of the way so that we can write our quotients off to the right-hand side. Let's go ahead and choose our pivot column. When there is a tie on the bottom row for the most negative, you can choose either. I'm choosing the first column, but you could choose either. Now we calculate our quotients. So on the right, here we have 14 over 2, which is 7. 26 over 2, which is 13. 28 over 1, which is 28. Choose the smallest quotient. And then that gives me my pivot row. And so here where they intersect, that's my pivot element, which I'll highlight. Now what we want to do is, remember your pivot element, you want that to become a 1. Sorry, my computer will not let me write it, so I'm going to skip that. We want to turn that into a 1 and everything else in that column into zeros. So what we're going to do is we're going to multiply 1/2 times that first row. And then I'm leaving the other rows for now. Let's put my columns back on here to make sure I didn't miss anything. As I just noticed that I did. That can happen when you have many columns. Let's check my first one again. I should have another 0 in the P column, and then 7 for the right hand side. Move to my second row. 2, 4, 1, 0, 1, 0, 0, 26. And then my third, 1, 2, 3, 0, 0, 1, 0, 28. These are all the same for now. Okay, and I'm highlighting my pivot element again so I can remember which one it is. It's right here. I've now turned that into a 1, and now I want to get zeros elsewhere in that column. In other words, I want to get a 0 here. I want all of these to be zeros. So now we're going to take the opposite of those numbers. So that'll give me -2 row 1 plus row 2 into row 2. We're going to do -1 row 1. So we're taking the opposite of that number, which is 1, multiplied by the row with the leading 1. And add it to that row. And so for the last one, 2R1, that's the opposite of that -2, times the row with the leading 1. Add it to row 4 and into row 4. This is a good place to remind you that you can never exchange rows when you are doing the simplex method. If you look back at your initial tableau and where your pivot element is, we know that we want to get a 1 in this place, and you might be tempted to switch the first row and the third row in order to get a 1 in that position. However, if you do this, that means you are essentially changing your pivot row from this first pivot row, which was calculated by doing the smallest quotient, 14 over 2 equals 7. If you just simply exchange rows, you would be essentially moving to an incorrect pivot row, and your simplex method would not come up with the correct answer. So while you can do that when you are using matrices to solve a system of equations, you cannot do that in the simplex method. we are going to get our 1 and our zeros in this very standard way. First, by multiplying the pivot row by the reciprocal of the pivot element, then obtaining the zeros by taking the opposite of those numbers, multiplying by the pivot row, and then adding to the current row. We're going to do that every single time. Don't do any row operations that are different from that, and you will be okay. So let's write our new tableau. Here is what we get. So my first row I have 1, 1/2, 1, 1/2, 0, 0, 0, and 7. Then I have 0, 3, -1, -1, 1, 0, 0, 12. Third row, 0, 3/2, 2, -1/2, 0, 1, 0, 21. And then for my very last row, 0, -1, 1, 0, 0, 0, 1, and 14. Notice that pivot element, that pivot column, has changed into a column that looks like it came from the identity matrix. Now we are going to look for the most negative on the bottom row, which will be right here. That gives us our pivot column. Now we go to the right-hand side and calculate quotients. 7 over 1/2 gives me 14. 12 over 3 gives me 4. 21 over 3/2 gives me 14. Remember, we want to choose the smallest, which will be this one, the 4. That's my pivot row. So that'll be my second row. I'm going to circle and highlight my pivot element. And then we are going to do another pivot. Okay, remember what we want to do is we want to get a 1 in that position, and we want to get zeros everywhere else in that column. So that means we're going to want a 0 here, and we're going to want zeros here and here. And so, as always, we're going to get the 1 first, and then we're going to get the zeros. So we are going to multiply that second row by 1/3. So that gives me 1/3 row 2 into row 2. Okay, and I'm going to keep these others for now. So my second row I have 0, 1, -1/3, -1/3, then +1/3, 0, 0, and 4. That 4 is that smallest quotient that I already calculated. I'm going to copy the last two rows exactly as they are. Again, I realize that the row operations are tedious. I've shown you how to do it here so that you can, but please, as long as you know you can do it by hand, feel free to use technology for most of the problems. in performing the pivot. Okay, let me highlight my pivot element again so I remember which one it is. There it is. It's that second element in the second column. So now I want to get zeros here, here, and here. So I'm going to do -1/2 times that row with the leading 1 plus the first row. And then I'm going to do -3/2 times that row with the leading 1 plus the third row. Fourth row, I'm going to take the opposite of that number, so +1, row 2, plus that row 4 into row 4. Okay, so I've labeled my columns. Now we do those row calculations. My first row, we'll write like this: 1 0 7 6 2/3, -1 6 0 0 and 5. Second row, we'll have 0 1, -1/3, -1/3, 1/3, 0 0 4. Third row, 0 0 5/2, 0 -1/2, 1 0 15. Last row, 0 0 2/3, 2/3, 1/3, 0 1 and 18. Okay, now we look at our tableau. Are there any negatives on the bottom row? No, there are not. So that tells me that I'm done pivoting. And I've reached the optimal solution. So now I need to figure out what that optimal solution is that is represented by this final simplex tableau. Okay, so we think of which ones are our non-basic variables that are being set equal to 0. So these are set equal to 0. And how do we tell? We look for junk in the columns. In other words, we are looking for those columns, not including the right-hand side, that do not look like columns in an identity matrix. Okay, so that would be x3, s1, and s2. So right now we have x1 equal to 0. No, I'm sorry, scratch that. I meant to say x3 equal to 0, s1 equal to 0, and s2 equal to 0 because these are non-basic. Okay, and then we also have our basic variables. These are the ones that do not have the junk in the columns. These are the columns that look like they came from an identity matrix. So these are x1, x2, s3, and p. So what do I get for those? These I find the values by reading off the right-hand side. So x1 is 5, x2 is 4. Look for where that 1 is in that column. x2 is 4, then S3. Look for the 1 in S3's column. It's in the third row, and so then I come over to the third row of the right-hand side. S3 is equal to 15. And P is equal to 18. This should say S3 right here. And P, those are our basic variables. So now we need to write the solution clearly. So we are going to say the maximum is P equals 18. And this is going to occur when, now what we need to write here are the values for our original variables. Our original model had x1, x2, x3 in them, and so x1 is equal to x5, x2 is equal to 4, x1 is equal to 5, and x3 is equal to 0. Junk in the column. It's a non-basic variable and is therefore set equal to 0. In other words, your final solution does not include the slack variables. It only includes the original variables. Sorry, my solution seems to have disappeared. Let's try again. x1 is equal to 5, x2 is equal to 4, and x3 is equal to 0. Sorry about that. Okay, I hope this helped you to understand the simplex method.